All right, we all ready now? So, electronegativity is the attractive force that an atom has for shared electrons. The trend is the same as the trend for ionization energy. So I'm just going to draw a little diagram here. Big, small. In other words, highest electronegativity is, who was it again? Fluorine. Lowest electronegativity is francium. All right, the word share, when we think of share, so it says how tightly an atom holds on to shared electrons, the attractive force that an atom has for shared electrons. The word share, honestly, when you think of just the word share, is that a pleasant, like words have kind of an emotion to them. Would you think of share as being a wonderful, sweet, pleasant word? You don't. That's interesting. Wow. You've had a bad sharing experience. In most situations, do you think of share as great? We're going to share your hat. Josh, you and I are going to share your hat, okay? It's a bad idea, I agree. You've used those toothpicks. Okay, but if we share those hats, if we share that hat, that ideal situation of sharing means he gets it for a day, I get it for a day. He gets it for a day, I get it for a day. Does that make sense? Is that what, I mean, isn't that what we think of when we think of sharing? Is that really how things are shared? No, not at all. Not at all. You have to go back to, well, honestly, how people are today, adults or kids, but I particularly think of little kids. Mine! That's mine! You know, that little defiant 2-year-old, mine! And then screams when you try to take it away. That's what we think of as sharing, really. But the word is beautiful. I mean, the word itself, my goodness, you know, you all these things I think of in my mind right now, you're going to share this together, and you're going to share that, and it just sounds gorgeous. But in reality, it's not that perfect. You get it today, I get it today. It just doesn't work that way. So, electronegativity is dealing with who gets. So here's that electron we are sharing. We're sharing this electron. Who gets this electron the most often is going to be who has the highest, what? Electronegativity. Now let's think about something. Yesterday, or Tuesday rather, when we were talking about ionization energy, and ionization energy referred, the concept or the reasoning behind ionization energy kind of went back to the size of the atom. Well, let's think again about the size of an atom. What charge does this electron have? What charge do electrons have? Negative. What is the opposite of negative? Positive, okay? So if you've got francium, and francium is this big fat atom, do you think when francium goes to share with fluorine, which is that atom, you think francium, when it goes to share with that atom, do you think we're going to be able to, do you think I'm going to be sharing that electron as tightly? Am I going to have the attractive force to that electron as fluorine over here has? What do you think? Fluorine's tiny, isn't it? Who's closer to that shared electron? Whose positive nucleus is closer to that shared electron? Fluorine or francium? Fluorine. So who is going to have the greater attraction to my electron, even though it might be we're sharing it per se? Who's going to have that greater attractive force? Fluorine is. Why? Because its nucleus is going to pull it to itself more than my nucleus, which is way over here, is going to pull it to me. Does that make sense? So when you say why, that's why. That's why. Now, I'm going to write all that down for you because in our class, you don't have to have it because I give you electronegativities. But you do need to know why. I mean, you should understand that concept. It's a simple concept of positive and negatives. Positive that's closer to a negative is going to have a higher attractive force for that negative. Does that make sense? So it should. I mean, hopefully that makes sense to you. Now, where is there a situation, and I should have looked into my old notes, but I sometimes get what I've done in 109 confused with 105. Have you all heard of Hofbrinkel? That's what I thought. Okay, I knew I'd done that. I just wanted to confirm. What does that mean? What's Hofbrinkel? Diatomic molecules. So Hofbrinkel are the diatomic molecules. Who are they? Fluorine, bromine, come on everybody. Bromine, iodine, come on. Nitrogen, chlorine. Hofbrinkel, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. How many are there? 7. There's 7 diatomic molecules. Okay. Now, that means hydrogen with its 1 electron is bonded to relationship. Absolutely. Why? Because this hydrogen has the same electronegativity as, does that make sense? Now, is that perfect sharing? Yes. Is hydrogen stable? Is oxygen stable? Is fluorine? Does that make sense now? Why are they stable? Because, man, they're not fighting over the electron. It's a perfect marriage. It's perfect. They're sharing. This is what your goal is, folks. That's the goal, is that perfect sharing relationship. And that's what happens in the diatomic molecules. That is also what happens when you have electronegativities that are less than 0.5 difference. Now, you don't have to write that down, but just so that you know, there are other scenarios where the electronegativity is not exactly the same, but it is close enough that they're sharing that electron equally. And those are very stable compounds. They're very stable. Okay, so what we are going to do today is deal with where we're going. While we talked about the electronegativity because it's a trend, and now we're going to go into sharing electrons. That's what we're going to spend the rest of the day talking about, is sharing electrons, how electrons are shared. Before we go too far, though, I am going to just show you Lewis dot notation. Actually, I'm not even going to. Just scratch that out. Forget that part. We're not even going to do it today. There's no need. It's interesting, but it's not something we need to do today with our time. So what we're going to do is we're going to talk about Lewis structures, and we're going to talk about how these electrons are shared in compounds. There's one thing I need to go back to, though. Nobody said anything about this, but I need to mention it. I made a comment how tightly an atom holds on to shared electrons in a molecular compound. I hope everybody understands that. Molecular compounds are made up of what kind of element? All what? Nonmetals. So what are they doing? Are they sharing electrons? Yes. And now we know they're not shared equally. We know that now. But then it says how they're holding on to shared electrons in a molecular compound or a polyatomic ion. Polyatomic ions have charges. But what are most polyatomic ions made up of? Are they made up of metals or nonmetals? Polyatomic ions, they're made up of nonmetals. Most of your polyatomic ions are made up of nonmetals. So how are they bonded together? They're bonded together with that same covalent bond. They're bonded together molecularly, sharing electrons. So in other words, let's just take, for instance, carbon dioxide, or no, let's take water. Let's just do water. Let's just do water. Water, really, we're going to learn this just in a few minutes. Water is H bonded to O bonded to H. It's really HOH. But when you put the H's together, we call it what? H2O. This bond right here, this is just a straight up molecular compound. That's what I'm doing first. This bond is sharing electrons. Who are they sharing electrons with? Hydrogen and oxygen. Now, who has the higher electronegativity? Oxygen does. So who gets these shared electrons more often? Oxygen. oxygen gets these shared electrons more often. In fact, just so you know, if you haven't paid any attention to it, who's the most electronegative? Look at your periodic table. Who's the most electronegative? Who's the next most electronegative? Oxygen. So unless you have fluorine in the compound, it's always oxygen that's the most electronegative. So anytime you've got oxygen in a polyatomic ion, so now let's take nitrate. This was nitrate. This is what nitrate looks like. Oxygen bonded to nitrogen, bonded, and then over here nitrogen bonded to another oxygen, and then nitrogen bonded to another oxygen. So my feet are one oxygen, this is an oxygen, this is an oxygen. That's what it looks like. But the overall thing has a charge of what? Come on, nitrate. -1. The overall thing has a charge of -1. Why? Because it's got an extra electron that had to be added to make it bond. Where did it get the electron? It doesn't matter. Maybe it got it from sodium. Would sodium like to lose an electron? Does that make sense? So that's what happens to make compounds. And then those polyatomic ions are not formed until the compound is being made. It's not like you have this group of polyatomic ions over here just waiting to be asked out on a date. They don't become the polyatomic ion until there is something else present to allow them to bond together and give the electrons that are needed to make that polyatomic ion. All right, so what we're going to do is we're going to spend time putting all these together with Lewis structures. Lewis structures are representations using dashes or dots for electrons around the symbols of the atoms to show how electrons are being shared or bonded. The goal is an octet. What's an octet? 8. Why is the goal an octet? So it looks like a noble gas. Does that make sense now that you've done electron configuration notation? Do we want a full S and P subshell? Is that the goal? Except for who? Hydrogen. Hydrogen only needs what? How many total? 2. So hydrogen only needs 2. Why does hydrogen only need 2? Guys, right here, fill that blank in. Why does hydrogen only need 2? Look up there. Look at what subshells hydrogen have. It only has what? S. It only has the S subshell. So why? Because hydrogen only has one energy level and S subshell can only hold 2 electrons. That's it. That's it. It can only hold 2. So hydrogen does not need an octet. Hydrogen needs a duet. Everybody else needs an octet. Okay? All right, so how can atoms bond? They can bond with a single bond, double bond, or triple bond. A single bond would be how many electrons, you think? No, 2. The bond. One party gives 1, the other party gives 1, that's the bond. So 2 electrons. Double is 4, triple would be what? 6. The dots would just be 2 dots, 4 dots, and 6 dots. And then the dashes are 1 dash, and then double, which is like an equal sign, and then a triple dash. We will use dashes for bonds. Use for bonds, and then the 2 electrons that are unbonded, the only time you'll use dots for unbonded electron pairs, also called lone pairs. So you're going to use dots when you have electrons that are not bonded. You'll use dots when you have electrons that are not bonded, and you will use dashes anytime they're bonded to something else. So the rules are listed for you there. Right now, I'm not even going to look at the rules though. Right now, we're going to just do the Lewis structures for the diatomic elements, which will hopefully help you start to see the ways they share, and then you'll be able to follow the rules better when we actually do some that need the rules. So I've shown you, or today rather, I've already talked to you about who the diatomic elements are. So tell me again who the diatomic elements are. That's why I always do it in order of Hofbrinkel. I always have to do them in that order. All right, so those are your diatomic elements. And how are they in nature? H, O2, F2, Br2, I2, N2, Cl2. Okay? So that's what they would look like in nature. So what we're going to do is draw the Lewis structures for all the diatomic elements first. And that will allow us to see what single, double, and triple bonds look like also, which will help. I've basically already shown you hydrogen. How many valence electrons does hydrogen have? Each hydrogen. Oh, do we need to go back over valence electrons? How many valence electrons does hydrogen, lithium, sodium, potassium, rubidium, cesium, francium have? 1. Valence electrons are what? What are valence electrons? Outer energy level electrons. Valence electrons are outer energy level electrons. Does that make sense? Where is the valence electron for hydrogen, lithium, sodium, potassium, rubidium, cesium, francium? In the S subshell, yes? How many electrons are there? Do we remember 1s2, 2s2, 2p6, 3s2? Remember this? This is what we're dealing with, okay? How many valence electrons are in beryllium, magnesium, calcium, strontium, barium, radium? Come on. 2. How many valence electrons are in boron, aluminum, gallium, indium, thallium? 3. Carbon family. Nitrogen family. The oxygen family. Halogens. 7. Noble gases except helium. 2. Everybody in the D and F subshell have how many valence electrons? Everybody in the D and F subshell have how many valence electrons? 2. They all have 2. Look. Everybody here, what do you have to say? 4s2 before you go down to 3d. What's the outer energy level for this? 4. 4 is the outer energy level. How many electrons are there? 2. What's the outer energy level for this? 5. How many electrons are there? 2. What's the outer energy level for this and these? 6. How many electrons are there? You follow what I'm saying? So everybody here has how many valence electrons? 2. All right, real quick. How many valence electrons? 5. 2. 7. 3. Okay, you got it then? You got to know this. You got to know. Because who plays a part in forming compounds? Who? Valence electrons. Why? Because they're out here. Are you going to make a compound with something that's way inside? Are you going to share electrons that are way down here close to the nucleus? Which electrons are going to be shared? The ones that are out here. Guys, you got to be with me today. The ones that are out here. The ones that are out here are the ones that are going to be shared, okay? Wake up. Get your brains on. Come on. All right, you're going to do this in lab next week. You're going to be doing this lab, VSEPR Theory and Lewis structures next week in lab. That's what you're doing. So pay attention today so you know what to do next week, okay? All right, so I'm going to just show you. Don't draw yet, just watch. And I'm going to use color just to kind of make it easy to see. All right, so blue hydrogen brought how many valence? Don't draw, just watch, listen. Blue hydrogen brought 1 valence electron, yes? Red hydrogen brought 1 valence electron, yes? Yes. Are they sharing these equally? Yes. So the actual Lewis structure, remember I said we use dashes for bonds? That's the Lewis structure. Okay? Why is it happy with 2? Because hydrogen only needs how many total? 2, because it's in the first energy level S subshell, yes? Okay. Everybody else needs how many? 8. All right. So now I've done hydrogen. Now I'm going to skip oxygen for a minute and go to fluorine. Just watch. Don't draw yet, just watch. I'm going to again use colors. Fluorine has how many valence electrons? 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. What do we have? Are they sharing those two? Does that make each fluorine happy? Yep. So what is that again? It's a single bond. So the Lewis structure for fluorine looks like this. That is the Lewis structure for fluorine. Get it away from that dot on the screen. That's the Lewis structure for fluorine. Okay? Now, on this problem, I want to ask you, how many bonds are there? 1. There's only one bond. There's only one bond. This is one bond. One bond. Now, how many lone pairs of electrons are there? 6. What's a lone pair? Unbonded pair of electrons. What's pair? 2. 2 is a pair, okay? So 1, 2, 3, 4, 5, 6. 6 lone pairs. That's what that would be. 6 lone pairs. These are questions that I may ask you on a test. How many lone pairs are around such and such? Okay? So you've got to be able to count. And remember, a pair is 2. Okay? Who else will look just like fluorine? Say it. Bromine, chlorine, and iodine. Why? Look. Look where they all are. Fluorine, chlorine, bromine, and iodine all have how many valence electrons? 7. Does that make sense? All right. So now we're going to follow the rules to do oxygen. And you'll see why in a minute, but let's go back and follow the rules. Okay. So the rules for drawing Lewis structures. Count the total number of valence electrons if an anion, if a cation is O2 an anion or cation. No, it's just oxygen. So we're going to do step 1. So we're drawing O2. This is what we're drawing, O2. So it says count the total number of valence electrons. So how many atoms do we have? 2. Times how many valence electrons does each have? 6. So that's a total of how many? 12 electrons. Now I'm going to make a little note here on what this is. This is number of atoms, and this is valence electrons. I'm just putting VE, okay? So that's number of atoms and valence electrons. That's what the 2 is number of atoms, and 6 is the valence electrons. I encourage you to put this on your paper, or at least revisit this, assuming it uploads properly, because you're not going to know what that means later, potentially. All right, so we have done step 1. Go to step 2. It says determine the central atom, usually the atom you have only one of, and usually the least electronegative. Do we have a true central atom with only 2 elements? No. So keep reading. Connect all the other atoms to the central atom using single bonds. So in our case, it just simply means attach oxygen to oxygen with a single bond. That's what it means. So attach oxygen to oxygen with a single bond. Step 3. Count the number of electrons used to form your single bond and subtract this number from the total electrons obtained from step 1. Folks, this is like when you use your debit card and you forget to account for how much money you just spent 3 days ago and your card's declined because you didn't do the accounting, that's what this is. You've got to account. You've used it. How many have you used? 2. You've used 2. So you must subtract 2 electrons because it was 2 electrons that were used. So how many do we have left? 10. So we have a 10 electrons left over. So that's step 3. Now go to step 4. Use the remaining electrons from step 3 to place in pairs, and it's very important you do pairs. Place in pairs around all atoms so that an octet is formed. Remember, hydrogen only needs 2, and also place electrons around the most electronegative atom first. Now, since both of these have the same electronegativity, we're just going to pick one and put them around it first. So how many do we have left over? 10. So 2, 4, 6, 8, 10. Everybody with me? Now, if there are not enough electrons to give each atom an octet, let's make sure where are we right now. Let's look at that oxygen. Is that oxygen happy? Does it have 8? But let's look at that oxygen. Does it have 8? No. How many does it have? 6. It only has 6. Does everybody understand 2, 4, 6? So it only has 6. So they're both not happy. So now we do have to read. If there are not enough electrons to give each atom an octet, rearrange the pairs of electrons to form double or triple bonds as needed. Electron pairs are taken from the atom that has the most and placed between that atom and the needy atom. In doing this, the atom that has the most to begin with, which will be here, doesn't lose anything, it's sharing. Do not add more electrons or take any away. So who has the most? The right one. So we're going to rearrange a pair of electrons and put them in the middle. So we redraw, double bond, like so. Now, cover up one. 2, 4, 6, 8. Is that right? Cover up the other one. 2, 4, 6, 8. Is that right? Now, before you say 100% sure, make sure you have 12 to begin with. 2, 4, 6, 8, 10, 12. So, boom. Yes, that's it. That is the Lewis structure for oxygen. Does that make sense? So that's how we form a double bond. So we've taken care of oxygen. The only one left is nitrogen. So, N2. How many valence electrons does nitrogen have? Good. So how many atoms of nitrogen do we have? N2. 2. Does that make sense? So we put 2 times 5 equals 10 electrons total. What's the next step? Come on. Bond them with a single bond. So we do N-N. Bond them with a single bond. How many electrons are we using? 2. So what do we take? 10 minus 2 is 8. So we use 2. That's 8 electrons left. Now, it says you place them in pairs around the most electronegative atom first. Well, they're both the same electronegativity, but you still put them all around one, then you put them around the other. Don't even them up. It will make things harder if you even them up, okay? So you put 2, 4, 6, 8. Now, if one of these was more electronegative, then you would have put them around the more electronegative. But in this case, they were the same, so you just put them all around one first. Now, confirm you still have 10. 2, 4, 6, 8, 10. Okay, so we haven't added, we haven't taken away. Is the right nitrogen satisfied? How many does it have? 8. Is the left nitrogen? No. So what do we need to do? The word is rearrange. We need to rearrange electrons. So the first thing you're probably going to do is make a double bond. If you make a double bond, does that immediately satisfy this nitrogen? And if you need to redraw it, you may, but how many does this nitrogen now have with that double bond? 6. So what are you going to have? A triple bond. So take another pair and move them, and then the Lewis structure is this. Yes or no? Okay, I'm going to talk about that. All right. So if you notice something that I did here, I actually had this pair of electrons down at the bottom when I was drawing it the first time, and then I moved it over here, and I did that on purpose. What are electrons constantly doing? Moving. They're constantly moving. The bond stays the same, but the electrons are constantly moving. In all actuality, electrons are going to be as far away from each other as possible, which we're going to learn about in a few minutes, called VSEPR theory. I don't care how you draw them. I did that on purpose to have this opportunity to say it doesn't matter where you put them as long as you keep them as a pair. That's the key. They must stay a pair. On your homework, it doesn't matter. It doesn't matter how you put them. And I will also tell you, if you're not doing that practice, which is like 20 questions long before you do your actual assignment, you're probably hurting yourself, because you need to learn how to rearrange and do all that bonding stuff on the homework program before you actually start the homework, and it will help you, okay? It's 5 extra credit points. So you get something for your effort to do it, but I think it will help you, okay? So I encourage you to do it. But realize there's also the homework 4 that's due. So make sure you do it as well. Does this make sense? Okay, so now we're going to use these rules to do more problems. So if you've, and the hints here, let me just go ahead and give you the hints. That way I don't have to refer back to the hints. So the hints are hydrogen, fluorine, chlorine, bromine, iodine only form single bonds. Hydrogen, fluorine, chlorine, bromine, and iodine only form single bonds. Why would that be? Why do you think that would be? They only need one more. They only need one more. Are they willing to share any more than one of theirs? No, that's what they're saying. No, we will only form single bonds because we're not willing to give up our own. We're going to keep 7 or 6, and we're going to let you share one of them with us. It is selfish. All right. Oxygen, sulfur, will form double bonds. So they'll form single and double bonds. Carbon and nitrogen form single, double, and triple. Not as selfish. Now, why aren't they as selfish? Oh, sorry. But they're also not as selfish. I'll send it in a minute. Why would these not be as selfish? They need more. They need more. They don't have very many to begin with, so they're willing to share everything they have, or most of what they have, in order to get a happy octet. So that's why. All right, so now let's go over to this page using your rules. Let's follow the rules. So what are the rules? What's the first step we take? Count the total number of valence electrons. So the first thing you have to know is, what is water? H2O. That's the first thing you have to know is the formula. So H2O. So we have 2 atoms of who? With how many valence electrons? Each hydrogen has how many valence electrons? 1. So 2 times 1 plus 1 atom of oxygen, and it has what? 6. So that's a total of how many? 8. So we have a total of 8 electrons. Yes or no? Okay. Who's the central atom? Oxygen has to be. So you put O, single bond it to the H's. Now I tend to draw everything in a straight line. You don't have to. You'll find out later they're actually not linear, but that's how I draw it. So how many electrons have we used? How many? Right here. Count. 4. Yes? Does everybody get that? How many are a line? 2. So 2, 4. So minus 4. How many are left over? 4 electrons left. Now, who gets them? The most electronegative. Plus, does hydrogen need them? No. Why does hydrogen not need them? How many does hydrogen need? 2. It's got 2, doesn't it? Yeah. So who gets those extra 4? Oxygen. So where are they going to go? Boom, boom. Now, did I not just stand here and do this? Did you see me do that? H bonded to O, bonded to H. I just didn't show you the lone pairs. Okay? So that's what water looks like. That's what water looks like. Now, let's just answer a few questions. How many bonds does water have? Say it. 2 bonds. How many lone pairs does water have? 2 lone pairs, or unbonded pairs. That's just something to kind of get in the habit of doing. Okay? All right, carbon dioxide. What's the formula for carbon dioxide? CO2. CO2 is the formula for carbon dioxide. All right, what is the number of carbon atoms we have? 1 times how many valence electrons does each carbon have? 4. Are we all together on that? Because I heard somebody say 6. Does everybody understand 4? Look at the periodic table. Got it? Okay. So 1 times 4 plus how many does oxygen have? 2 atoms of oxygen. How many valence electrons? 6. So what's 4 plus 12? 16 electrons total. Yes or no? Okay. All right. Who's our central atom? Carbon. Oxygen will hardly ever be a central atom. The only time it's a central atom is in water and probably in oxygen difluoride. That's the only time you'll ever see it as a central atom. Every other time, oxygen is going to be on the outskirts because it's the most electronegative. Okay? So, carbon will often be a central atom. Often, carbon will be a central atom. In 107, when you all get into 107 next semester, you're going to spend a lot of time. That's all your whole 107 class is going to be about, is carbon chemistry, basically. And that's what you're going to deal with. Lots of structures and lots of compounds with carbon. That's what the whole course is, organic chemistry. So carbon single bonded to oxygens. How many electrons did we use? 4. Is everybody with me? So subtract 4. How many are left over? 12 electrons left over. Who will get them first? Why? Most electronegative. How many times have I said today? Who's the most electronegative other than fluorine? Oxygen. Who's going to take the electrons? Who's going to share the electrons? Who's got the stronger attractive force for electrons? Oh, oxygen does. All the time. It's pulling those electrons to it. So give it to them. 2, 4, 6, 8, 10, 12. Now, some of you say, okay, that was easy, we're done. Somebody else better say, no, we're not. We're not done. Why are we not done? Carbon is not happy. Carbon is not happy. How many valence electrons does carbon need? No. 8 total. It needs 8. It needs 8. How many does it have? 4. So yes, it needs 4 more, but it needs a total of 8. Now, we have 2 options. We can form what? We can form a double bond. So let's just do that. Let's form a double bond. So move a pair, form that double bond. I'm just going to write it below it. Same thing, just rewrite it right below it, except with that double bond. So that's step 1 of our process. Or I guess this was step 1, this is step 2. Trying to figure out. Did the right hand oxygen still keep 8? Yes. Did carbon gain a total of, does it have 8 now? How many does it have now? 6. Does the left oxygen still have 8? Yes. So it helped, but it didn't solve the problem. No. So what's a choice to do? What can we do? Could we put a triple bond? Let me ask you a question. Could you put a triple bond? Would that solve the problem as well? It would. Do you know why you don't? You're correct that you don't. We form another double bond. Look back at your hints. Look at your hints. Look at your hints. What did I tell you on your hints? Oxygen what? Single or double. Can oxygen form a triple bond? No. That's how you know it's 2 double bonds. Oxygen will not form a triple bond. That's how you know. So you must form another double bond. So what you end up with is carbon in the middle, 2 double bonds. Now, before you say, yes, I'm done, count everything again. 2, 4, 6, 8, 10, 12, 14, 16, that's correct, and each has 8. And then I like to circle my answer to say, yes, I'm done. Yes or no? What, Lucas? Speak up, honey. Speak up. I can't understand you. The what? One. Each carbon has 4. Each oxygen has 6. So 2 oxygens times 6 is 12. 13, 14, 15, 16. Does that make sense? You're saying, why is this 16? 2, 4, 6, 8. Each line means 2. 2, 4, 6, 8, 10, 12, 14, 16. Is that it? Okay. All right, nitrate. Let's do an ion together, and then I'm going to have you do a couple, and then we're going to go to the VSEPR theory. Nitrate. What's the formula for nitrate? NO3. Keep going. negative 1. You must have the charge. NO3 negative 1. NO3 negative 1. Guys, I will not give you ions on your test. Your test is Tuesday. If you don't have your ions memorized, just like in your midterm this week, you're kind of up a creek. Okay? You need to know your ions. All right? You need to know your ions. All right, 1 times what? Valence electrons. 1 times 5 plus 3 times 6. Now, it's a negative 1 charge. Go back to the rules. What do we do when it's a negative 1 charge? What do we do when it's a negative 1 charge? What's it say? If it's an anion, you do what? Add electrons equal to the charge. Because it has an extra electron, right? So what do we add? Plus 1. And I draw an arrow to say, hey, that's due to that charge that we're adding that 1, so that you have that in your notes for later. So 5 plus 18 is 23, plus 1 is 24 electrons total. Yes or no? All right. Who's the central atom? Nitrogen. How are we going to bond these? First, single bond to each of the oxygens. Yes or no? All right. How many electrons have we just used? 6. So we're going to subtract 6 because we used 6 for those single bonds. I'm going to make a note here. Used in single bonds. How many are left over? 18 electrons. Who will get them first? Oxygen, because it's the most electronegative. And as you can see, if you can do some math in your head, each one will get 6. So we look at that and say, wow, that's easy. But is it happy? Who's not happy? Nitrogen's not happy. So what must you do? Form a double bond. Does it matter where? Does it matter from which one? Left, right, bottom? Does it matter? No, it doesn't matter at all. Pick one. Pick a pair, move them in between. So I picked that pair and then rewrite it. So I'll let you get caught up on this. So let's double check. So look what I did. Look at the bottom. Did I move that pair? Do you see that? I moved this pair in between nitrogen and oxygen. Yes? We follow? So that's the double bond. Now count. How many should we have total? 24. So 2, 4, 6, 8. 2, 4, 6, 8, 10, 12. Whoops, shoot. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22. I can't count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. You need to learn how to count by twos. Okay? Is it still 24? Yes. Now, what do we put around this to show the reader we had to add an electron? We put brackets. This is very important. You must do this. So you put brackets around the whole thing, and that says to the reader, I had to add an electron. I had to add an electron. Yes or no? All right, phosphite. What's the formula for phosphite? P-O what? What charge? Minus 3. PO3 minus 3. Good. PO3 minus 3. I'm going to be quiet and let you try it. You've done 3 with me. Try this. Follow the rules. All right, PO3. Here's what you should have. That's the answer. How many of you got it? Good job. Good job. Guys, some of you need to pay attention, okay? You got to do things with me. All right, let's look at it. How many phosphoruses do we have? How many? 1. Each phosphorus has how many valence electrons? 5. Plus, how many oxygens do we have? 3. Each has how many valence electrons? 6, yes? Why do we add 3? Because it's got a -3 charge. So 5 plus 18 is 23, 26 total, yes? Everybody get 26 total? Even if you didn't finish it, did you get 26 total? Okay. Who's going to be the central? It's going to be the least, so it's going to be oxygen always on the outside. So single bond, that took up how many? 6. That leaves us how many left? 20. Now you've just done one that had 18 left, and you put them around the 3 oxygens, so that you if you're thinking, you know, okay, that's going to take 18. Who's going to get the last 2? Who needs them? Phosphorus. Do you need to do a double bond? No. No triple bond, no double bond. You have enough. Everybody's happy. Put brackets -3. This one is easier than the nitrate. Yes? Sometimes I think students get in the habit of, oh, I got to form a double. No, you don't. You don't have to form a double bond if you don't need to. Why do you want to share anything in your own life if you didn't have to? If you had your own clothes and you have a sister who has her own clothes, do you really need to share clothes? No, not unless you just want to, but you don't have to. Okay? All right, ammonium. What's the formula for ammonium? NH4 what? +1. NH4 +1. Do it. Do it. Let's finish it. For those of you still not following, one atom of nitrogen, it has 5 valence electrons plus 4 atoms of oxygen, 1 valence electron. Now you have to do what? Subtract 1 because of the positive charge. It has lost an electron. That leaves 8 left over. Who's the central atom? Nitrogen. Hydrogen can never be a central atom. Why can hydrogen not be a central atom? It only needs how many? 2. How many do we use here? How many have we used? 8. So what do? Subtract 8. There's nothing left over. Folks, you're done. Put a +1 on it. That's it. Everybody get that one? All right. I'm going to give you the formulas for these, but then we're going to flip to do VSEPR, and then we'll come back to this, okay? Let me give you the, actually, I shouldn't have to. You tell me. What's the formula for phosphorus trichloride? PCl3. Phosphorus P. Cl3 is trichloride. Carbonate ion. CO what? -2. Good. CO3 -2. Chlorate. ClO3 -1. Okay? And we'll come back to these. Hopefully you'll have time. But I'll definitely draw them on here. But let's flip the page and get through VSEPR theory. All right, VSEPR theory. VSEPR theory is it's an acronym, and it stands for valence shell electron pair repulsion theory. All right, let's dissect that. Valence shell. What's the valence shell? Outer energy level. Valence shell is the outer energy level, yes? Valence shell electron pair. What's a pair? 2. First of all, let's ask this question. How can electrons exist in pairs? How do they exist in pairs if they both are negative? Negatives repel each other anyway. So how are they even existing in pairs? What are they doing? Spinning in what? Are they doing this? Are they doing this? No. What are they doing? Spinning in opposite directions. That's how they exist in pairs. That's how they exist in a pair. So you have outer energy level electrons, 2 spinning in opposite directions, outer energy level electron pairs doing what to each other? What does the word mean? What's repulse mean? Ooh, yuck. Get away, yes? Something's repulsive to you. Is that how you are? What's repulse mean? It means repel. Get away. So what do outer energy level electrons that exist in pairs do to other outer energy level electrons? Push them away. They push them away. So what this is saying is this is a theory that basically helps us understand the shape of molecules. Now, something that may seem a little foreign to you, because it's kind of beyond me at times, it definitely is beyond me all the time, but I accept it as true. Your body has all kinds of molecules in it, all kinds of ions in it. Some of those go certain places in your body and they don't go other places, right? Your hormones know exactly where to go, exactly what to target, and exactly what to do. Your enzymes know exactly what to help with to make the reaction work. All of that is so much related to the shape of the molecule. The shape of the molecules determines where that's going to go and where it's going to fit in your body. There are certain things that will not cross the blood-brain barrier because they can't fit, because the shape of the molecule. All of that's related to shape. Okay, now we're dealing only with 5 shapes though. We're dealing with 5 geometrical shapes. There are a lot more. We're only learning these 5, and I keep it super, super simple. Okay, if you had a high school chemistry class higher level than this one, you learn more shapes than this. But we're only learning 5. And those 5 are linear, bent, trigonal planar, trigonal pyramidal, and tetrahedral. Those are my 5 shapes that we're learning. Linear, straight line. Everybody get that? Straight line. Linear is a straight line. Now, here are the rules for linear, though, and I keep it really, really specific for you. Linear may contain 2 to 3 atoms. It can have single, double, or triple bonds. Here's the key. Look what it says. No lone pairs where? Around the central atom. That's the key. No lone pairs around the central atom. Obviously, are all diatomic molecules going to be a straight line? Because there's only 2 of them, right? Now, it also tells you carbon dioxide. Now, look back at carbon dioxide. Find carbon dioxide in your notes. Find carbon dioxide in your notes. How does carbon dioxide fit that? Does it have 3 atoms? Yes. But tell me about the central atom. No lone pairs. So what shape is carbon dioxide? Linear. Carbon dioxide is linear. Literally, not literally, I should not use that word, but this is carbon dioxide. Okay? What am I holding up here? What's up here? Oxygen. What are these? Double bond. What's this? Carbon. And what are those? Double bond. And down there I'm standing on who? Oxygen. Is there any lone pair anywhere around here? So what shape am I? Linear. Because these bonds are repelling each other so much that it's making it straight. Does that make sense? That's why. That's why that happens. Okay? Are these as far away from each other as they can be? Yeah. That's why that happens. Okay? All right, go to bent. Bent. Very specific for you. Bent contains 3 atoms. It may have single or double bonds. But here's the key. What's it say? It will have 1 to 2 lone pairs around the central atom. It will have 1 to 2 lone pairs around the central atom. It will have that. And then I give you water. And then I give you water. So go back and look at water. Now, I drew water linearly. And I told you when I drew it, I usually draw things straight. Doesn't matter how I draw it. It's what it really is. What is it? What shape is this really? It's bent. Why is it bent? Due to lone pairs. It's bent due to those lone pairs. So think about when I stood here and did this. I said, who's this? I'm water. Hydrogen bonded to oxygen, bonded to hydrogen. But up here, I wish I had little dots I could put up here. Right here is what? A lone pair. Right here is a lone pair. Are you with me? So what is this lone pair doing to this lone pair? What's it doing? It's bending it. It's bending it. It's bending it down. And you got to remember, it's like 3-dimensional. It's bending it down. Does that make sense? Because they're trying to get away from each other as much as possible. So it's probably, I can't do it. You're going to get to do this in lab next week. You get to do little balls and sticks, okay? So that's what you're going to see. So it's bent. All right, keep going. These get more fun as we go. Keep going. All right, trigonal planar. Trigonal planar is extremely specific. What's it going to have? 4 atoms and what? Specifically, 2 single bonds, 1 double bond, no lone pairs around the central atom. You've already seen me do this one. Who is it? Nitrate. Look over here at nitrate. What do you have right there? What did you see me do earlier today? Did I do this? Who am I? Nitrate. I'm nitrate. What is this? A single bond bonded to oxygen. What's this? Single bond bonded to oxygen. What's this? Double bond bonded to oxygen. Now, is there any lone pair here or anywhere else? No. Now, the whole thing is you got to understand it's three-dimensional. So it would be more like this. It's going to be twisted. But is there anything that's bending this down? No, because there's no lone pairs. So that is trigonal planar. That's trigonal planar. Okay, you can draw carbonate later. That helps you know what carbonate is going to look like if you're thinking. All right, trigonal pyramidal. I'll call it trigonal pyramidal. Properly, it's called trigonal pyramidal. Again, extremely specific for you. It contains 4 atoms, only single bonds, 1 lone pair. 1 lone pair around the central atom. 1 lone pair. Now, I haven't given you either one of those two, so you're going to get the pleasure of drawing those later for yourself, which I hope you will do. But let's come over here. Do we have a trigonal, oops, I didn't write this on here. This is trigonal planar. Probably want to write that. Trigonal planar for nitrate. Now, we've got 2 left. Do we have a trigonal pyramidal? Who is it? Phosphite. Do you see that? Do we have 1, 2, 3, 4 total atoms? Do we have single bonds and 1 lone pair around the central atom? You follow? So who is this? Trigonal what? Trigonal pyramidal, trigonal pyramidal, however you want to say it. That's what that is. Basically, if you'll think about what's happening here, imagine the trigonal planar. Now pretend that this is now a single bond, okay? So now you have this as a single bond, not a double bond. So just pretend my legs are a single bond. But what's this? What is that? Look at phosphate. This is phosphate. What's that? The lone pair. What's that lone pair doing? What's it doing? Pushing it down. It's pushing it down. Now, what would happen if I'm shaped like that? Does that look like a pyramid? Does that make sense? That's where it's getting its name. That's looking like the pyramid, trigonal pyramidal. All right, the last shape, the easiest one because it's the only one that has 5 atoms. The only one in our class that has 5 atoms. Only single bonds, no lone pairs. And I give you 2 choices again we haven't drawn. I want you to do this for practice on your own. I'll put the answers on here and leave it running so you'll have that to look back at. Now, guess who's tetrahedral? Ammonium. Ammonium is tetrahedral. So tetrahedral. That is tetrahedral. How many total atoms do we have? 5 total atoms. And no single bond, no lone pairs, all single bonds, right? So, here, I'll just do it for you. Since you're probably my last class, I'll just do the grand show for you, okay? I probably can't do it. I used to do this all the time. So, what you would do is, you see this? And I can't do it worth spit anymore. It's pretty better than I thought I could. So, what's happening though? Is this a single bond, and I'm totally cockeyed here, but do you get the point? But the problem is it's not like this, it's twisted. Does that make sense? And you'll get to draw this. You'll get to draw it, okay? So the whole thing is twisted. So body VSEPR, you got the whole show this year, okay? Body VSEPR. All right, so now, what I want you to do, you got 4 minutes. Here's what I want you to do. I want you to draw phosphorus trichloride real quick. Finish them all up. Finish them all up. If you've got time, finish them all up. I'm going to go ahead and finish lecturing here. Don't leave until I say go. But I'm also going to add these on this page so that you can then, if you need to watch the video or at least get the answers, you'll have that to help you study, okay? But let's go ahead and do phosphorus trichloride. So phosphorus, how many atoms do we have? Atoms. 1 times 5 valence electrons plus how many chlorines? Times, good. So how many total is that? 26 electrons total. Guys, have we already done one with 26 electrons total? Do you start to see the patterns here? You're going to do the same thing over and over again if you're paying attention. Who's the central atom? Phosphorus. What do? Single bond it. Now don't get in too big of a hurry. You still follow the rules. How many do we use? 6. Subtract 6. That leaves 20. Who's going to get them? The chlorines first. And then we're going to have those 2 left over. Who gets those? Phosphorus. So that is your answer for phosphorus trichloride. What is the VSEPR geometrical shape? What's the VSEPR geometrical shape for that? Trigonal pyramidal. Trigonal pyramidal or trigonal pyramidal. Good. All right, carbonate ion. 1 times 4 plus 3 times 6 plus 2. Why do we add 2 electrons? Due to the charge. Guys, if you're really not understanding this, don't just copy it just to hurry up and get it copied. Wait and watch the video and really think about it, okay? So then 18 plus 4 is 22, 23, 24 total. Have we done another one with 24 electrons total? So you're going to have the same thing again. So carbon in the middle, single bond to the oxygens, minus 6, leaving 18. Give them to oxygen first. You notice carbon is not satisfied, so you're going to have to form a double bond. It doesn't matter where you form it from. Double bond, one of those, single bond the rest. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and everybody has 8. Brackets around the whole thing because it's a charged ion. And what shape does it have? Trigonal planar. Chlorate, 1 times 7 plus 3 times 6 plus 1 due to the charge. 26 again. Have we seen that before? Yes. So Cl in the middle. If you also are thinking about the hints, you know chlorine cannot what? Chlorine can't have more than one bond anyway, so it would have to be brackets around the whole thing because you used all, I'm sorry, I didn't follow my rules here. That left you with 20, and brackets around the whole thing, -1 charge. What's the VSEPR shape? Trigonal what? Be careful, not planar. Trigonal pyramidal. Trigonal pyramidal. All right, go ahead and go. I'm going to go ahead and draw the ones that you don't have drawn on this VSEPR theory, and then that'll be on the video, hoping everything uploads properly. Okay? I'll see you on Tuesday. Bring a calculator. Bring a calculator. You always have dimensional analysis, at least one on every test. Bring a calculator. All right, both of these are on the sheet. On sheet. All right, all those are on the sheet. So nitrogen trifluoride, NF3, and ASO3, -3. So 1 times 5 plus 3 times 7, that's 26 electrons total. And we've done this several times now, so nitrogen Bond it to fluorine. Use 6. That leaves 20 left over. And as you can see, fluorine will get them first. And then nitrogen. So this is nitrogen trifluoride. On arsenate, it's 1 times 5 plus 3 times 6 plus 3. So that's 26 electrons also. You've just done one like that. So arsenic in the middle. Subtract your 6, leaves 20. Same thing we've been doing. Brackets around the whole thing. -3. Methane, CH4 is 1 times 4 plus 4 times 1. You can see that's 8 valence electrons. Carbon's in the middle. Pretty simple on that one. That's it, because you used all 8 up. And then phosphate is 1 times 5 plus 4 times 6 plus 3. That is, let's see, 5 plus 3, so 24, 25, 67. I'm not adding right. What am I doing wrong here? Yeah, 32. I'm not adding right, am I? 32 total. Yeah, 32 total. All right, so phosphorus in the middle, single bond, subtract 8, 26 electrons left, 24 electrons left over, and that makes sense to give each oxygen 6. So brackets around the whole thing, -3. All right.